Welcome friends, I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable and ready to wander with me into the long cold story of a comet that carries the oldest materials in the solar system, Comet Hale Bopp. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The narration flows seamlessly into the darkness of space, where a faint point of light begins its slow emergence from the vast reservoir of icy bodies surrounding the sun. Hale Bopp appears long before it becomes bright enough for human eyes. It moves inward from a distance so immense that sunlight has almost no effect on it at first. The scientifically accepted fact grounding this moment is simple. Hale Bopp originates from the Oort Cloud, a region tens of thousands of astronomical units from the sun, populated with trillions of icy bodies left over from the formation of the solar system. Only took the lingering remnants of early planetary scattering to populate a sphere larger than the orbits of stars in some clusters. The comet's motion at these distances feels almost indistinguishable from stillness. Orbital speeds drop to a crawl so slow that entire civilizations could rise and fall before the comet makes meaningful progress. Hale Bopp spends most of its time in these far-off regions where temperatures hover near absolute zero, and sunlight arrives as a faint suggestion rather than illumination. Only took the loosening of the sun's grip to stretch a single orbit across tens of millennia. A poetic detail emerges in imagining the comet's visibility from this distant vantage point. Its nucleus is coated in dark carbon-rich material, so black that it reflects only a small fraction of the light that touches its surface. From nearby it would appear not as a gleaming ice ball, but as a charcoal-coloured world drifting through endless night. Only took a thin layer of organic dust to turn sunlight into something the nucleus mostly swallows. And drifting around this nucleus is uncertainty, a quiet scientific mystery that remains unresolved even now. Hale Bopp's brightness during its 1997 apparition was far greater than expected for comets of similar size and distance, suggesting either unusually volatile rich material or internal structures that remain unknown. No mission has ever visited it. No probe has sampled its composition directly. Its secrets remain sealed in ice older than any planet. Only took one comet with unexpectedly vigorous activity to remind scientists that even well-studied objects can defy simple explanation. As the narration moves inward, the comet begins responding to sunlight more noticeably. Even at extreme distances, molecules such as carbon monoxide, far more volatile than water, can sublimate into gas. This sublimation creates a thin atmosphere around the nucleus, a coma so faint it would be invisible to instruments until the comet approaches the realm of the giant planets. Only took a shift of a few degrees in temperature to begin the process that shapes every visible comet. The coma forms not as a sudden burst, but as a slow exhale escaping through porous textures and tiny cracks in the comet's crust. Dust grains embedded in the ice lift free and drift around the nucleus in clouds that scatter sunlight. Their motions are slow, almost circular, forming patterns shaped by rotation rather than winds, for winds do not exist here. Only took the absence of air to let dust float without falling. Hale Bopp continues drifting inward along its long elliptical orbit. Its path carries it from deep space toward the sun, yet the sunlight that reaches it is still weak. The ice responds gently. There is no rush. Sublimation increases inch by inch, day by day, following the comet like a soft halo that grows so gradually it seems as though it has always been there. Only took the smallest rise in solar energy to awaken a world that slept for millennia. A poetic detail surfaces in the comet's motion. Comets do not travel straight toward the sun. They follow curved trajectories shaped by gravity, alone tracing elliptical paths that reflect the delicacy of orbital mechanics. Hale-Bopp's orbit is unusually stable and elongated, taking more than 2,000 years to complete one full revolution. Only took a single scattering event in the early solar system to place this comet on a path stretching across epochs. Scientific uncertainty enters quietly here as well. The precise history of Hale-Bopp's orbit remains partly unknown. Its perihelion distance, the closest point to the Sun, has shifted over time due to gravitational encounters with Jupiter and Saturn. Some models suggest close interactions thousands of years ago altered its return interval. Others propose earlier disturbances in the Oort Cloud itself. Only took one planetary encounter lost to history to adjust the comet's schedule for millennia. As Hale-Bopp edges closer to the Sun, the coma's expansion reveals more subtle processes. Dust particles become electrically charged under sunlight, aligning and repelling in patterns that form the structures later seen in photographs. Jets from active regions on the nucleus rotate with the comet, creating spirals that trace the object's spin rate. These spirals remain faint and delicate, observable only through careful imaging. Only took a slow twirl of a cometary core to etch patterns of dust across thousands of kilometers. A modern analogy may rest gently here. The coma behaves like breath, forming in cold air, invisible at first, then slowly condensing into shapes carried outward by imperceptible currents. Hale-Bopp's breath, however, stretches across millions of kilometers, influenced not by air, but by radiation pressure and the solar wind. Only took a star's faint push to sculpt the first outlines of the tails that will soon follow. The narration lingers on the nucleus again, roughly 40 to 60 kilometers across, far larger than the typical cometary core. This size contributes to its brightness, its longevity, and the richness of its volatile ices. Larger nuclei possess more internal heat from radioactive decay in the early solar system, allowing differentiation and the formation of layered structures. Only took the quiet decay of ancient isotopes to shape the interior of a body drifting unnoticed for ages. Yet even now, uncertainty remains surrounding Hale-Bopp's exact size. Observations place it within a range, but cannot yet narrow it definitively. Its rotation period, measured from the behavior of dust jets, offers clues, but not certainty. Only took the sheer distance and darkness of a comet's life to hide details that telescopes strain to uncover. As Section 1 draws toward its conclusion without shifting tone or pace, the comet continues its silent journey toward the inner solar system. Nothing dramatic occurs. The coma expands. Dust drifts. Volatile molecules slip from ancient ice into open space. Everything happens slowly, evenly, without urgency. Only took the long patience of deep time to bring Hale-Bopp's ancient nucleus into a region where sunlight can finally reveal its presence. The space around remains quiet. The stars keep their positions. The comet moves with a rhythm older than recorded history, carrying dust grains older than Earth itself. And the narration prepares to follow it inward toward the tails that will soon bloom behind it, toward the bright apparition that once astonished the world, and toward the deeper mysteries still sealed beneath its frozen crust. The narration moves forward with the same slow, even breath that carries Hale-Bopp inward, letting the comet's transformation unfold without haste. Here the guiding sensation becomes the gentle awakening of ancient ice, a process controlled not by sudden heat, but by increments so small they resemble the quiet shift from shadow into dawn. The scientifically accepted fact grounding this moment is that comets begin releasing volatile gases long before water ice warms enough to sublimate, because compounds such as carbon monoxide and carbon dioxide evaporate at far lower temperatures. Only took the faint touch of sunlight at dozens of astronomical units to start stirring molecules that slept for billions of years. As Hale-Bopp drifts inward, sublimation remains almost imperceptible, yet the nucleus begins to shed material one molecule at a time. This slow exhale builds the thin, ghost-like beginnings of the coma, a haze of gas and dust barely tethered to the nucleus by gravity. Dust grains drift outward, gently forming patterns determined by rotation and the geometry of illumination. A poetic detail emerges in the way sunlight strikes these grains. Each particle reflects only a faint glimmer, yet together they create a blurred aura around the nucleus, as if the comet carries a soft lantern that brightens gradually with distance. Only took the alignment of countless tiny grains to form a glow visible from across millions of kilometers. The narrator observes how the coma expands in all directions, creating a sphere around the nucleus, even while the comet remains far from the sun. But the sphere is not uniform. Subtle differences in the composition and porosity of the comet's surface produce uneven sublimation, forming jets that release dust and gas from specific regions. Only took the uneven texture of ancient ice to send material flowing from one patch more readily than another. A quiet scientific mystery rests within these jets why Hale Bopp displayed such strong activity at such extraordinary distances. No other comet observed has shown comparable vigour so far from the Sun. The comet was already visibly active beyond 7 astronomical units farther than Jupiter, a place where most comets remain silent. Some researchers propose unusually high concentrations of carbon monoxide. Others suggest a surface rich in fresh volatile ices, exposed by previous perihelion passages. Only took one unknown internal structure to create an activity level that challenged expectations. As the coma grows, the comet begins to interact more noticeably with sunlight. The dust grains respond first. Solar radiation pressure pushes them gently, and the combined effect of countless grains drifting backward begins to form the foundation of the dust tail. This tail does not yet appear as the long sweeping arc familiar from photographs. Instead, it forms as a faint extension of the coma, widening slowly as the comet approaches the warmer layers of the inner solar system. Only took the steady pressure of photons to begin shaping a tail that will eventually stretch millions of kilometers behind the nucleus. The ion tail emerges differently, formed not by drifting dust, but by molecules stripped of electrons through interaction with ultraviolet light and the solar wind. These ions feel the influence of the sun's magnetic field carried outward by the wind itself. The tail begins as a thin ribbon, narrow and bright, always pointing directly away from the sun regardless of the comet's direction of motion. A poetic detail arises in its behaviour. If the dust tail is a trail, the ion tail is a compass needle, unwavering, aligned by forces too faint to feel, but too persistent to ignore. Only took the steady flow of the solar wind to sculpt a tail that behaves with perfect geometry. As Hale Bopp moves inward, its coma thickens, forming layers of structure shaped by rotation. Jets emerging from active regions sweep through space as the nucleus spins, creating spiral patterns that drift outward like expanding corkscrews. Observations in 1997 revealed these spirals, clearly a rare chance to see a comet's internal rhythm encoded in the geometry of dust. Only took a 6 to 7 hour rotation period to imprint spirals across tens of thousands of kilometers. A modern analogy may gently rest here, just as a rotating lighthouse sweeps its beam across darkness. The comet's jets rotate, carving luminous arcs that reveal its spin even from vast distances. Only took a slowly turning nucleus to send luminous signals spiraling across space. The narrator lingers on a lesser-known detail. Hale Bopp's coma exhibited sodium emissions, creating a rare yellowish tail distinct from the dust and ion tails. This sodium tail stretched millions of kilometers, composed of neutral atoms pushed outward by solar radiation pressure. Neutral sodium tails are incredibly rare and were only confirmed in a few comets. Only took the right blend of minerals and illumination to reveal a tail invisible to most but detectable in sensitive spectral imaging. Yet uncertainty surrounds this sodium tail as well. Sodium atoms originate either from dust grains heated just enough to release embedded elements, or from surface materials broken apart by sublimation. The exact source remains debated. Only took the presence of a few spectral lines to raise questions that have yet to be resolved. The comet brightens slowly as it travels inward, Reflective dust increases, volatile gases expand the coma, and sunlight intensifies. But brightness does not increase smoothly. It pulses in slight variations tied to rotation, surface composition, and jet orientation. Observers in the 1990s noted these fluctuations, which helped measure the rotation period of the nucleus. Only took the alternating exposure of active and inactive regions to produce rhythmic brightening across hours and days. As the temperature rises modestly, new volatile species awaken. Carbon dioxide sublimates. Methanol and other organic molecules vaporize. The coma becomes chemically rich, filled with compounds that formed in the earliest stages of the solar system. Bopp released more than 24 identifiable molecules, including some found in interstellar clouds. Only took the right combination of ancient chemical pathways to preserve molecular structures predating the Sun. The narrator follows Bopp inward to the region halfway between Jupiter and Mars, where sublimation becomes vigorous. Water ice, the most abundant component of cometary nuclei, finally begins to evaporate. Water molecules stream outward, carrying dust grains that scatter sunlight more efficiently. The coma expands dramatically, becoming visible to the naked eye from Earth long before the comet approaches perihelion. Only took the awakening of water ice to turn a silent wanderer into one of the brightest comets of the century. Yet even here, scientific uncertainty holds softly. Estimates of the comet's water production rate vary widely. Measurements suggest an output up to 40 tons per second at peak activity, but the exact numbers remain imprecise because the coma's brightness depends on sunlight dust density and viewing angle. Only took the complexities of illumination to make precise measurements challenging even for advanced telescopes. A poetic detail appears in the tail's curvature. The dust tail bends gently along the comet's orbit, because dust responds both to solar pressure and to the comet's direction of motion. The ion tail, however, remains nearly straight, swept into alignment by the solar wind. Side by side, the tails create the characteristic forked appearance that made Bopp so striking during its 1997 apparition. Only took the interplay of dust and plasma to create a celestial form that seemed almost sculpted. As Section 2 approaches its close, Bopp continues drifting inward, silent and steady. The coma grows wider. Jets spill outward. Dust settles into slow arcs. Molecules escape from cracks that have not seen warmth in 10,000 years. Nothing rushes. Nothing leaps into change. Everything unfolds in the slow rhythm set by distance, temperature and rotation. Only took the long patience of cold space to craft the gentle brightening of a comet returning from the dark. The narrator remains with this quiet transformation, ready to follow the comet as the sun's influence deepens toward the dazzling tails, the bright apparition visible across Earth, and the deeper mysteries still embedded in Bopp's ancient ice. The narration moves onward with the same slow steadiness as Bopp itself, letting the comet's twin tails unfold in the quiet geometry that has guided its motion since the earliest days of the solar system. By now, the comet has drawn close enough to the Sun for its activity to intensify, and the change is subtle but unmistakable. The coma thickens, the dust brightens, and the space behind the nucleus begins to separate into two distinct streams. The scientifically accepted fact grounding this moment is that comets develop both dust and ion tails, each formed through different physical processes, one driven by sunlight's pressure on solid grains, the other sculpted by the solar wind interacting with ionized gas. Only took the simple physics of light and plasma to shape structures stretching millions of kilometers across space. As Bopp continues its inward drift, the dust tail grows first. Dust grains freed from the comet's surface vary in size from micron-sized particulates to larger fragments, tens of micrometers across. The smaller grains respond quickly to solar radiation pressure pushed outward with an acceleration that lifts them away from the coma. The larger grains lag behind, following more closely the comet's orbital path. A poetic detail emerges in the way this separation forms a soft gradient of brightness. Fine grains forming the tail's diffuse outer regions, larger grains forming its inner spine. only took the difference in grain size to paint the tail with subtle gradations of light. The dust tail bends gradually along the comet's orbital curve, shaped by the interplay between solar radiation pressure and the comet's forward motion. The curvature becomes a natural marker of direction, a gentle reminder that comets do not simply plunge sunward, they arc through space along elliptical paths defined by ancient gravitational histories. Only took the comet's inherited orbit to guide dust into a long sweeping arc rather than a straight line. The ion tail behaves differently. Ionized molecules such as CO+ and H2O+ form when ultraviolet photons strip electrons from gas emitted by the nucleus. These ions feel the influence of the solar wind, a stream of charged particles flowing outward from the Sun at hundreds of kilometers per second. The ion tail forms nearly instantaneously along magnetic field lines, embedded in the solar wind pointing directly away from the Sun, regardless of the comet's direction of travel. A poetic detail reveals itself in this unwavering alignment. The ion tail acts like a silent pointer, a cold compass needle oriented by forces that never rest. Only took the gentle flow of plasma from the Sun to control the direction of an entire celestial structure. A quiet scientific mystery lingers gently here. Hale-Bopp's ion tail displayed unusual kinked structures during its 1997 apparition, likely caused by interactions with transient solar wind disturbances, such as coronal mass ejections. Yet the precise timing and details of these interactions remain only partially understood. Ion tails respond so sensitively to magnetic field fluctuations that interpreting their shapes requires models more complex than those available at the time. Only took the unpredictable breath of the Sun to imprint patterns whose full meaning remains partly hidden. As the comet comes closer still, the two tails become more pronounced, creating a vivid, forked appearance against the background stars. The dust tail appears broad, white and soft, illuminated by sunlight reflecting off billions of particles. The ion tail appears narrower and pale blue, glowing through fluorescent emission from ionized gas. The difference in color reflects real physics. Dust scatters sunlight, while ionized gas emits narrow band light as electrons recombine with their parent molecules. Only took the contrast between scattering and emission to give the tails their distinct hues. The narrator observes a poetic detail in the way the two tails separate clearly from each other. The comet's motion through the solar wind creates a slight angle between the tails, as if the comet carries two delicate banners, one pulled backward by light itself, the other stretched by plasma. This separation does not require turbulence or violence. It arises from differences in physical response. Only took two simple interactions, light on dust, wind on ions, to create a double structure that seems as intricate as brush strokes. As Hale-Bopp brightens, the coma expands and thickens, becoming large enough to appear as a small sphere even through modest telescopes. Observers in 1997 noted the coma's diameter exceeding 1 million kilometers, at times larger than the Sun despite its faintness. Yet the nucleus at its center remained shrouded, hidden behind the dense outflowing material. Only took the density of escaping gas to mask a world only tens of kilometers wide, beneath a sphere of light thousands of times larger. The narrator moves gently to the inner coma, where dust spirals continue tracing the comet's rotation. These spirals reveal the nucleus's spin period, measured to be roughly 11 hours. As jets emerge from fixed locations, they sweep around through the coma, imprinting faint arcs that drift outward. Over time, these patterns become difficult to distinguish, as gas pressure blurs them, yet for a brief interval they reveal the comet's internal rhythm. Only took the comet's slow rotation to paint temporary structures that reveal the hidden mechanics beneath its crust. A lesser-known poetic detail emerges: sunlight interacting with the dust produces forward scattering effects, making the comet appear brighter from certain angles. This behavior caused Hale-Bopp to surge in brightness, as viewed from Earth before and after perihelion, contributing to its reputation as one of the brightest comets of the 20th century. Only took the angle between Earth comet and Sun to amplify the glow of dust grains already illuminated, yet within this glow lies uncertainty. Brightness measurements varied significantly among observers, partly because the dust coma's structure fluctuated subtly over time, and partly because the comet's high production rates caused complex interactions between dust and gas. The exact contribution of dust versus gas to the comet's overall brightness remains debated. Only took the complexity of mixed materials to make even simple brightness curves challenging to interpret. The narrator watches as the comet continues inward, carrying its double tail behind it. The dust tail lengthens dramatically, eventually stretching tens of millions of kilometers. The ion tail extends even farther, sometimes exceeding 100 million kilometers, depending on solar wind conditions. But length is not uniform. Solar storms compress or stretch the ion tail, altering its shape and brightness. Only took fluctuations in the solar wind to reshape a structure whose physics remains at its core astonishingly delicate. As Hale-Bopp approaches the orbit of Mars, its activity intensifies. Water sublimation becomes dominant, dramatically increasing gas output and dust release. The coma becomes richer, denser, more textured. Jets erupt with renewed strength. The tails widen and brighten. The comet now resembles the object that would astonish millions of observers on Earth in 1997, though in this narration, its rise remains gentle, stripped of spectacle, and framed in the patient language of physics. Only took the warming effect of the sun to turn a silent wanderer into a bright visible presence. Section 3 closes slowly, letting Hale-Bopp continue its measured path inward. The dust tail drifts behind like a pale river of light. The ion tail points away with quiet precision, and the coma glows softly as sunlight reveals the materials carried across deep time. Nothing accelerates, nothing disrupts the calm. Every change remains gradual, shaped only by heat light and the slow persistence of orbit. Only took the steady approach toward the inner solar system to allow the comet's twin tails to unfurl, fully ready for the next chapter of its luminous journey. The narration drifts inward, with Hale-Bopp settling now upon the nucleus itself, the dark, compact core from which all the comet's luminous structures arise. Even as the coma grows wide and the tails stretch across millions of kilometers, the true comet remains only a few dozen kilometers across. Here the sense of scale contracts dramatically, while the significance of this small ancient body expands. The scientifically accepted fact grounding this section is that cometary nuclei preserve some of the oldest solid materials in the solar system, formed from the primordial dust and ice present in the protoplanetary disk more than 4.5 billion years ago. Only took the earliest freeze of the solar system's ingredients to ensure that a small drifting world would outlive continents, oceans, mountains, and entire epochs on Earth. The nucleus of Hale-Bopp, though hidden beneath the coma, has been studied through careful modelling of brightness variations and gas output. Its shape is not perfectly spherical. The surface likely carries slopes, depressions, and overhangs formed through billions of years of sublimation and refreezing. A poetic detail emerges in imagining this nucleus not as a glowing orb, but as a deeply shadowed carbon black object, its surface darker than coal, its contours softened by accumulated dust. Only took a thin layer of radiation-processed organics to mute the reflection of sunlight almost entirely. The narrator follows the comet as it rotates slowly, revealing subtle complexities in the pattern of its jets. These jets emerge from discrete vents, fractures, or porous regions where sunlight reaches pockets of volatile ice. As the nucleus spins, the jets sweep across space, creating spirals that drift outward through the coma. The rotational patterns measured through changes in brightness reveal a nucleus roughly 50 kilometers in diameter. Only took the flicker of jets across the coma to deduce the heartbeat of an object too small and distant to see directly. A quiet scientific uncertainty lingers around the nucleus's exact dimensions and mass. Observations from Earth-based telescopes and the Hubble Space Telescope offer estimates, but no spacecraft has ever visited Hale-Bopp up close. Its density, internal layering, porosity, and geological history remain topics of active study. Only took the absence of an in situ mission to ensure that the comet retains most of its secrets, despite intense observation. As Hale Bopp nears the orbit of Mars, the sun's warmth penetrates deeper beneath the surface layers. Water ice trapped for millennia under the crust of dark organics begins to sublimate more vigorously. Gas pressure builds beneath the surface and escapes through vents with more force. Dust is carried outward in thicker plumes, forming complex structures in the inner coma. Only took a few more degrees of warmth to awaken materials untouched since the solar system's youth. The narrator senses the interior processes that shape this activity. The nucleus likely contains regions of pristine ice, interspersed with layers of dust and rock. Some pockets may have been sealed since the comet's formation, preserving chemicals in their original state. When these pockets open, they release bursts of material rich in volatile species such as carbon monoxide, methane, and hydrogen cyanide. A poetic detail rests in the possibility that some molecules escaping now were trapped before any planet existed. Hydrogen cyanide formed in interstellar clouds or carbon-based compounds, synthesized in the cold chemistry of the protosolar nebula. Only took the resilience of simple molecules to survive the collapse of a star-forming cloud and remain preserved inside a wandering comet. Uncertainty deepens when scientists model the comet's unusual brightness. Hale Bopp exhibited high levels of activity at distances where most comets remain dormant. The reason remains incompletely understood. One hypothesis suggests an unusually volatile rich composition, perhaps containing ices that sublimate at extremely low temperatures. Another proposes that the comet's previous perihelion passage exposed fresh material more vulnerable to the sun's warming. Still others consider the possibility of internal heating from radioactive decay early in its history. Only took one unknown variable in composition or structure to create differences that remain unresolved decades after the comet's passage. The narrator lingers on the organic compounds within the nucleus. Observations of the coma revealed complex molecules such as formaldehyde, formic acid, and simple hydrocarbons, a chemical archive from the earliest days of the solar system. Experiments on Earth show that ultraviolet light acting on these ices can produce prebiotic molecules, suggesting that comets may have delivered key ingredients to young planets. Only took a distant storehouse of primordial ice to carry the same molecules found in star-forming regions light years away. A poetic detail arises in imagining the surface of the nucleus as a mosaic of textures and tones, rough crustal slabs, fine dust, embedded pebbles and patches where volatile rich layers lie just beneath the surface. When sunlight strikes these regions, thin jets form like exhalations, momentary and ephemeral. The nucleus rotates, and the vents shift in and out of illumination, giving the comet a pulsing, rhythmic outflow that shapes every structure around it. Only took the slow turning of an ancient body to orchestrate the dance of gas and dust that follows. As the comet draws nearer to the inner solar system, its activity begins to carve subtle features on the nucleus itself. Sublimation erodes the surface, forming small pits and hollows. Dust left behind accumulates in low regions, creating smoother, darker patches. Over successive orbits, these features would evolve, but Hale Bopp's long period means it rarely returns to the inner solar warmth. Only took a single close passage to reshape surface terrain that will remain frozen and unchanged for thousands of years. The narrator considers how little of the comet is visible even now. The bright coma obscures the nucleus completely. What scientists know about the core comes indirectly from the way the coma behaves, the way dust spirals drift, the way gas jets fluctuate. This indirect approach reveals broad characteristics, but conceals fine details. Only took the veil of the coma to hide the nucleus behind a shell of its own breath. Yet within this hidden core resides a gentle irony. The nucleus, so small compared to the structures around it, controls everything. The coma, the tails, the brightness, the observable beauty all emerge from this cold, dark body. Only took a few dozen kilometers of ancient ice to create a display stretching across millions of kilometers. A second irony rests in the fact that the nucleus is the least luminous part of the comet despite being the source of its light. Only took the darkening effect of organic dust to make the origin appear dimmer than the structures it creates. And a third irony lies in the nucleus's endurance. While gas and dust escape at enormous rates, the core itself loses only a small fraction of its mass during each perihelion passage. Hale-Bopp's enormous size means it can endure many more returns before losing significant volume. Only took a larger than average nucleus to guarantee survival across ages. As Section 4 nears its quiet end, the narrator allows the nucleus to remain hidden, wrapped in its expanding coma. The comet continues inward. The rotation remains steady. Jets puff and fade. Dust drifts outward. The nucleus, unchanged in appearance, continues shaping the luminous structures surrounding it with patience older than any landscape on Earth. Only took the persistent rhythm of ancient ice warming under sunlight to carry Hale-Bopp deeper into the inner solar system where its next transformations await. The narration moves onward with Hale-Bopp as it follows its long elongated path inward, tracing an orbit that spans millennia. Here the sense of scale stretches farther than the tails themselves, drawing attention to the celestial architecture that governs the comet's journey through the solar system. The scientifically accepted fact grounding this section is that Hale-Bopp travels along a highly elliptical orbit exceeding 2,000 years in duration, carrying it from the cold periphery of the Oort Cloud into the warm inner solar regions before sending it back into deep darkness. Only took the gravitational sculpting of the early solar system to cast a comet into a trajectory that bridges epochs. The narrator follows this orbit back to its origins. Hale-Bopp did not form where it now begins its journey. Instead, it originated much closer to the Sun during the chaotic early phase of planetary formation. Interactions with the growing giant planets scattered countless icy bodies outward, trapping some in the vast reservoir now known as the Oort Cloud. Hale-Bopp became one of these distant wanderers, its orbit reshaped by gravitational encounters and nudges from passing stars. Only took a close pass near Jupiter or Saturn billions of years ago to eject the comet into a nearly interstellar trajectory. A poetic detail emerges in imagining the early solar system as a place of constant collisions and migrations, planetesimals drifting, spiraling, scattering, merging and dispersing. The comets that survived this turbulent era became time capsules preserving conditions lost to planets that grew differentiated and resurfaced themselves countless times. Only took survival through chaos to turn a drifting ice fragment into a witness of the solar system's infancy. Hale-Bopp's orbit measures tens of thousands of astronomical units at its farthest reach. At aphelion, its speed slows to a crawl, moving so gradually that even the turning of the galaxy around its centre feels more immediate than the comet's motion. Only took distance from the Sun to let motion stretch into geological and cosmic timescales. The narrator moves gently along this elliptical path, sensing how gravitational forces shape its curvature. Kepler's laws define the relationship between the comet's distance and velocity. It speeds up near the Sun and slows down in the distant dark. The vast majority of its time is spent in cold stillness at the orbit's outer extreme, where the Sun becomes just another bright star among many. Only took the simplest gravitational law to choreograph a dance that lasts thousands of years. Yet within this grand arc lies scientific uncertainty. Hale-Bopp's orbital period is estimated to be between 2,000 and 2,500 years, but precise calculations depend on small gravitational influences that accumulate over millennia: planetary perturbations, galactic tides, and subtle pulls from passing stars. Only took the unpredictable drift of nearby stars to make the details of a single comet's return perpetually uncertain. As the narration continues inward, the narrator lingers on the gravitational dynamics that shape the comet's path. Each time Hale-Bopp enters the inner solar system, its orbit risks alteration through encounters with the giant planets. Even distant interactions can adjust its trajectory slightly, changing the timing or path of its next return. Only took a small gravitational nudge from Jupiter to rewrite the comet's long-term journey. Hale-Bopp's orbit is unusually stable, however. Unlike comets that pass close to Jupiter and risk capture collision or deflection, Hale-Bopp does not cross paths with the gas giant. Instead, the comet's trajectory carries it safely through a region where gravitational interference is mild. This stability is one reason why the comet's orbit will likely remain long-lived. Only took a fortunate alignment to spare the comet from chaotic gravitational reshaping. The narrator moves gently to a poetic detail about the orbit's shape. It is elongated but smooth, stretching like a thread pulled taut between two vastly different realms. Near perihelion, the comet moves fastest, diving toward the Sun with increasing speed. But even here its motion is not sudden. Acceleration is gradual, governed strictly by distance. Only took the approach toward the Sun to convert potential energy stored for millennia into swift but silent motion. At this stage in its inward path, Hale-Bopp begins to influence the region it travels through. Dust released earlier drifts along the comet's orbit, creating a diffuse meteoroid trail that will persist long after the comet is gone. Over time, such trails contribute to the zodiacal cloud, the thin disk of dust that scatters sunlight across the inner solar system. Only took the passage of a single comet to add another faint layer to the luminous material encircling the Sun. The narrator drifts outward mentally to consider the scale of the Oort Cloud, the comet's birthplace. The Oort Cloud is believed to extend up to a light year from the Sun, forming a loosely bound sphere of icy objects shaped by the gravitational influence of the Sun planets, nearby stars and the Milky Way's tides. Hale-Bopp's origin lies within this realm where trillions of icy bodies orbit slowly, disturbed only occasionally by passing stars or large molecular clouds. Only took a distant stellar encounter to send a comet inward for the first time in tens of thousands of years. Scientific uncertainty envelops the Oort Cloud, for no object within it has ever been observed directly. Its existence is inferred from the behaviour of long-period comets. Hale-Bopp becomes one of the few direct messengers from this remote region, carrying composition clues from a place too distant to study with telescopes. Only took the path of a returning comet to reveal a structure visible only through its departing members. As Hale-Bopp continues inward, the Sun's influence strengthens gradually. The comet accelerates slightly, its orbit curving more noticeably. The scale of space begins to compress from thousands of astronomical units toward hundreds. The comet enters a region where solar radiation and wind exert measurable effects, driving sublimation-shaping tails and altering particle trajectories. Only took the threshold crossing from the outer system to the inner realms to allow solar energy to begin its transformative work. A poetic detail arises in the idea that Hale-Bopp's orbit is a long, cold breath exhale from the distant dark inhale near the Sun and return to the silence beyond. The sublimation of ices becomes like a planetary exhale, releasing ancient materials into the solar wind. Only took the inward sweep of an orbit to turn a frozen archive into a drifting cloud of dust and gas. As the narrator watches the comet approach the orbit of Mars, the orbital mechanics become more pronounced. Hale-Bopp's trajectory tilts 15 degrees relative to the ecliptic plane, a reminder that comets do not follow the orderly flat paths of planets. This inclination means the comet travels through regions of space planets never touch. Only took a slight tilt in the orbit to separate the comet's path from the familiar solar plane. Yet even here, subtle gravitational influences continue shaping its motion. Mars contributes a barely perceptible pull. Jupiter adjusts the comet's path through its distant influence. Saturn draws faint arcs into the orbit's curvature. Over millennia, these minute forces accumulate. Only took insignificant tugs repeated endlessly to reshape the orbital future of a comet travelling across time. As Section 5 approaches its quiet close, Hale-Bopp moves with increasing confidence toward the inner solar system. It has travelled from the coldest reaches of the Sun's influence, carrying ices older than any mountain on Earth, along a path defined by gravity alone. Now the warming glow of the Sun beckons, ready to transform the comet into a luminous visitor visible across Earth's skies. Only took the ancient architecture of the comet's orbit to guide it toward a moment of brightness in a journey dominated by darkness and distance. The narration continues with Hale-Bopp as it draws nearer to the Sun, and the quiet awakening of its internal ices becomes something more dynamic, though still entirely unhurried. Here the guiding sensation becomes the comet's steady exhalation, not a burst, not a flare, but a prolonged and ancient breath released from beneath layers of dust that have not felt warmth for thousands of years. The scientifically accepted fact grounding this moment is that sublimation intensifies as a comet approaches the sun, driven not only by the warming of surface layers, but also by the penetration of heat into deeper pockets of volatile rich ice. Only took the slow conduction of heat through a porous crust to transform trapped ice into gas after an age of perfect stillness. Hale-Bopp's jets strengthen gradually. Gas escapes from vents in the nucleus with greater force, carrying dust particles of varying sizes that drift outward into the coma. This dust broadens the coma and enhances its visibility, scattering sunlight more effectively. A poetic detail emerges in the way these grains lift from the surface, not as explosions but as faint geysers that loft fine particles into space with movements so slow they resemble drifting ash. Only took the simple expansion of warming gas to raise grains kept in darkness since before Earth formed. As activity increases, the inner coma becomes more structured. Regions closer to active vents glow slightly brighter, forming asymmetric shapes within the otherwise spherical cloud. Dust jets emerge like pale plumes tied to the rotation of the nucleus, imprinting spirals that drift outward and dissolve into the broader haze. Only took the comet's slow spin to give the coma its subtle, ever-changing architecture. A quiet, scientific mystery rests here. Why Hale-Bopp produced such extraordinarily high levels of gas and dust compared with most comets. Estimates suggest the comet's gas output at peak activity exceeded 200 tons per second, enough to sustain its brightness across vast distances. Yet the exact internal composition and structure enabling such strong activity remain partly unknown. Only took an unusual mix of volatile rich layers to create outgassing beyond normal expectations, though the precise layers remain concealed beneath the coma. The narrator lingers on the chemistry released from these sublimating ices. Observations detected dozens of volatile molecules: water, carbon monoxide, carbon dioxide, methane, ammonia, methanol, formaldehyde, and more complex organics. These compounds do not emerge in equal quantities. They reflect the comet's layered structure, with more volatile species sublimating earlier and deeper reservoirs, awakening only as the sun's heat penetrates more fully. Only took the gradual lifting of thermal energy to reveal a chemical record stretching back to the solar system's earliest days. A poetic detail surfaces in the temperature contrast between escaping gas and surrounding space. The gas emerges warm enough to move quickly at first, then cools rapidly as it mixes with the coma, forming microscopic ice crystals that shimmer faintly in reflected light. Only took the silence of deep space to freeze each escaping molecule almost instantly. As the gas continues to expand, it forms the broad inner region of the coma, where velocity slows and collisions between dust and gas begin shaping more complex motions. These interactions generate a boundary known as the collisionless zone, farther from the nucleus, where particles drift freely without interference. Only took increasing distance from the nucleus for the coma's physics to shift from fluid-like density to near-perfect emptiness. Hale-Bopp's dust production reaches levels seen only in the brightest comets. Dust grains lifted by the jets drift outward, forming layers and sheets within the coma. The grains vary in composition: silicates, organics, and carbonaceous materials, each responding differently to sunlight. Some scatter light efficiently, adding a soft white glow. Others absorb more light, creating subtle shadows and gradients. Only took the compositional diversity of ancient dust to paint the coma with as much texture as structure. A modern analogy settles gently here. The coma behaves like a slow-motion cloud, expanding outward from a source that never ceases but never erupts. But unlike any terrestrial cloud, it forms and evolves in a vacuum shaped not by wind or gravity, but by radiation, pressure, magnetic fields, and molecular collisions. Only took the absence of atmosphere to give the coma its delicate, unearthly behaviour. As the comet moves past the orbital distance of Mars, the increased sunlight alters the balance between gas and dust. water sublimation peaks forming a strong isotropic outflow. The nucleus warms enough for deeper pockets to release previously trapped volatiles. Jets erupt more vigorously. The coma brightens and expands, at times reaching millions of kilometers across. Only took the sun's strengthening warmth to turn a faint haze into a dominant feature. Meanwhile, gas escaping from the nucleus begins forming the ion tail with greater intensity. Molecules ionized by solar ultraviolet radiation react quickly, guided into alignment with the solar wind. This growing tail narrows into a long stream glowing faintly blue. Its straightness contrasts sharply with the dust tail's gentle curvature. A poetic detail arises in the way the ion tail flashes with ribbons and knots during solar wind disturbances, subtle waves drifting along its length. Only took a distant solar storm to ripple through a structure stretching tens of millions of kilometers away. Yet scientific uncertainty remains in the timing and origin of these waves. While models predict that coronal mass ejections and magnetic field fluctuations shape ion tails, the precise interactions depend on variables that are rarely measured directly at the comet's location. Only took the complexity of plasma physics to keep many details beyond direct observation. Dust continues to accumulate behind the comet in a broad tail. Larger particles follow the comet's orbit closely. Smaller grains are pushed farther outward by solar radiation pressure. The dust tail appears soft, diffuse and luminous, composed of countless particles scattering light in all directions. Its shape changes slowly, responding to the comet's position, relative to the sun and the surrounding solar wind. Only took the persistent push of sunlight to maintain a structure that would otherwise dissipate into interplanetary space. As Hale Bopp moves still closer, it approaches the region where it will soon be visible from Earth. Its coma now exceeds 1 million kilometers in diameter, its dust tail extends across tens of millions of kilometers, and its ion tail reaches even farther. Yet despite this immense display, the nucleus remains hidden, still only a dark speck at the center of all the outflowing activity. Only took a small core of ancient ice to generate a luminous presence filling an entire region of space. A quiet irony emerges the brighter the comet becomes, the more invisible its true body is. The nucleus's darkness contrasts sharply with the structures it produces. Only took millions of reflecting grains to overshadow the actual source. A second irony lingers in the fact that sublimation, which erodes the nucleus, also ensures its long-term survival, removing only small fractions of mass compared with the vast volume of the core. Only took steady minimal erosion to preserve the comet across thousands of returns. And a third irony rests in the comet's essential fragility. Despite its luminous power, the nucleus is porous, lightly bound, capable of breaking apart under stresses far smaller than those endured by planets or moons. Only took the right rotational torque or thermal stress to risk fragmentation. As Section 6 draws its slow, uninterrupted close, Hale Bopp continues in its inward glide. The sun brightens, the coma thickens, the dust tail lengthens. The ion tail glows faintly in soft blue. Everything unfolds according to rhythms set billions of years ago, with no haste and no deviation. Only took the steady rise of solar energy to coax the comet into its fullest visible form as it approaches the inner solar system and the site of the waiting Earth. The narration moves gently with Hale Bopp as it drifts deeper into the inner solar system, letting the growing brightness of the comet settle into view. Here the guiding sensation becomes the widening presence of its twin tails, but especially the ion tail, which now responds with exquisite sensitivity to the sun's outflowing wind. The scientifically accepted fact grounding this moment is that the solar wind, a stream of charged particles, moving outward at hundreds of kilometers per second, interacts directly with a comet's ionized gases, forming a tail that always points away from the sun regardless of the comet's motion. Only took the quiet persistence of the sun's invisible breath to sculpt a pale blue stream millions of kilometers long. As Hale Bopp approaches the warming region between Mars and Earth, sublimation continues to intensify. Molecules that evaporated earlier now ionize more frequently under ultraviolet radiation. Carbon monoxide becomes CO plus water, molecules become H2O plus and OH plus, and a cascade of simple molecules enters the realm of plasma. These ions drift outward with the solar wind forming the narrow limb of the ion tail. A poetic detail emerges in their behaviour. Each ion emits a faint glow in characteristic wavelengths, when excited by sunlight, creating a cold luminescence that imbues the tail with a soft blue colour. Only took the absorption and re-emission of sunlight by charged molecules to paint the ion tail with its quiet, ethereal hue. The narrator senses the purity of the ion tail's alignment. It does not bend gently like the dust tail. It does not follow the comet's curved path. Instead, it forms a straight, unwavering ray pointing directly away from the sun. This rigidity reflects the magnetic structure of the solar wind carried outward as a spiral created by the sun's rotation, the Parker spiral. The comet's ions become trapped within these magnetic field lines, forced to follow them outward. Only took the twisting magnetism of a rotating star to determine the direction of a comet's most delicate structure. A quiet scientific mystery lingers around the ion tail's subtle features. During its 1997 apparition, Hale-Bopp's ion tail appeared fragmented at times, displaying disconnections and kinks. Scientists attributed these events to shifts in the solar wind and transient magnetic disturbances possibly linked to coronal mass ejections. Yet the exact timing, shape, and recovery of such disconnections remain difficult to model. Only took a change in field strength thousands of kilometers wide to break a tail millions of kilometers long, and only for a moment. As Hale-Bopp moves nearer the sun, these disturbances grow more frequent. The solar wind strengthens and weakens depending on the sun's activity cycle, and the comet's ion tail responds almost instantly. Waves ripple along its length. Ribbons of brightness drift through it. Segments detach and fade. Yet despite these fluctuations, the tail's essential structure remains steady. A poetic detail appears in the way these ripples resemble faint whisper lines, travelling across a distant sheet of light so delicate that even slight variations create visible effects. Only took the sun's restless outer atmosphere to send quiet pulses down a filament stretching across space. Meanwhile, the dust tail behaves differently, slower, softer, broader, and its increasing brightness creates a stark contrast with the narrow, pointed ion tail. The narrator lingers on this contrast as a reminder that comets embody two distinct interactions: solid grains pushed by sunlight and charged molecules drawn by plasma. Only took these two processes working side by side to give Hale-Bopp its iconic forked appearance. Closer now, the comet produces an increasing flux of ions. Hydrogen atoms released from water undergo photodissociation, forming hydrogen atoms that escape into space at high speeds. These hydrogen atoms create a vast but invisible hydrogen cloud, stretching millions of kilometers around the comet. Although not visible to the naked eye, it represents the largest structure associated with Hale-Bopp. Only took the splitting of a water molecule to create an envelope that dwarfs even the dust and ion tails. A poetic detail emerges in the fate of lighter ions such as H+. These particles sometimes accelerate away from the comet so swiftly that they outrun the solar wind, entirely merging into the broad heliospheric environment. They become indistinguishable from the solar plasma lost to the vast flow of charged particles moving outward. Only took a single photon striking a water molecule to send atomic fragments into permanent flight. The narrator gently turns toward the chemical richness of the ion tail. Unlike the dust tail, which varies mainly with grain size and illumination, the ion tail shifts in composition as the comet warms. Some molecules appear only briefly as the necessary temperatures and pressures activate deeper layers. Others spike in abundance when particular jets rotate into sunlight. Still others fade because they photodissociate quickly, leaving behind only a faint spectral signature. Only took the interplay between sunlight chemistry and rotation to create a tail that tells time through its changing composition. Despite Hale-Bopp's vibrant activity, scientific uncertainty remains about the exact chemical pathways inside the nucleus. The presence of abundant CO+ in the ion tail suggests large stores of carbon monoxide ice within the comet. But the distribution of this ice, whether uniform or layered, remains unknown. Only took the absence of emission to the comet's surface to leave its internal geology a subject of quiet speculation rather than clear measurement. As Hale-Bopp approaches its brightest phase, the ion tail becomes more sharply defined. Its edges sharpen, its brightness increases, and its length becomes more pronounced. All across Earth, its pale blue filament becomes visible from dark skies. Even those unfamiliar with astronomy notice its strange straightness compared to the sweeping dust tail. Only took the right angle between Earth, comet and Sun to make the ion tail appear almost like a blade of cold light cutting across the sky. The narrator pauses briefly on an irony embedded in the tail's shape. The ion tail seems solid and steady, yet it is composed of particles so sparse that even the emptiest terrestrial vacuum would be dense by comparison. Only took a near vacuum to form a structure appearing strong enough to be drawn across the heavens like a line of glass. A second irony rests in the tail's impermanence. Though it stretches millions of kilometers, the lifespan of any individual ion is brief, measured in minutes or hours before it recombines, dissipates, or drifts away. The long arc visible from Earth is the result of constant replenishment rather than persistence. Only took the continuous exhalation of the comet to sustain a tail that seems unbroken. A third irony lies in the subtle fact that the ion tail's straightness makes it appear like a guide pointing outward, but it points not to where the comet has been, nor to where it is going, but simply away from the sun. Only took the unceasing direction of the solar wind to impose an orientation with no connection to the comet's path. As Hale-Bopp continues inward approaching the orbit of Earth, the narrator senses the growing harmony among its components. The dust tail widens, glowing warm and soft, the ion tail sharpens, glowing cold and straight, and the nucleus releases ancient gases into the immense expanding coma. Every feature responds to the sun, yet each reacts differently. Only took the unified pull of sunlight to create a structure that appears complex but is rooted in simple, unchanging physics. Section 7 draws toward its quiet end as the comet nears the region where Earth will soon witness its luminous form. The ion tail continues to glow faintly blue, unwavering, patient, shaped only by the solar wind and the properties of ancient molecules escaping from the nucleus. Nothing rushes, nothing jolts, everything unfolds with the same slow precision that defined Hale-Bopp's journey from the outermost dark. Only took the comet's gradual approach to let its most delicate structures reveal themselves fully as it comes into the sightline of an entire planet waiting for a quiet visitor from deep time. The narration moves onward with Hale-Bopp as it enters the region where its drifting dust begins to interact more deeply with the inner solar system, letting each particle released from the nucleus become part of a wider, longer-lived structure. Here, the guiding sensation becomes the slow dispersal of material tiny grains, leaving the comet forever taking with them a record of ancient chemistry and becoming part of the soft haze that fills the space between planets. The scientifically accepted fact grounding this moment is that dust released by comets contributes directly to the zodiacal cloud, the broad disk of particulate matter that scatters sunlight and creates the faint zodiacal light visible from Earth before dawn or after dusk. Only took the escape of a few grains from a distant comet to add new threads to a glow that humans have observed for millennia without knowing its origin. As Hale-Bopp continues its inward journey, the dust grains released from its surface do not all follow the comet's path. The smallest grains, only a few micrometers across, feel the strongest push from solar radiation pressure. They drift outward, falling behind the comet, then dispersing into broad diffuse sheets. Larger grains linger closer to the orbital path, moving more slowly under the combined influences of gravity, sunlight, and the comet's original momentum. A poetic detail emerges in how these grains form structures so faint and gentle that they behave almost like a mist trailing through interplanetary space. Only took the slightest push from sunlight to spread dust across millions of kilometers, The narrator observes how these drifting particles gradually lose any sense of belonging to a single source. Grain by grain, they become part of the interplanetary medium, a sparse collection of solids orbiting the Sun in a diffuse disk. Some grains spiral slowly inward under the effect of Poynting-Robertson, drag a process in which sunlight gradually steals orbital energy from dust, causing it to drift toward the Sun over millions of years. Only took the faint absorption of sunlight to place each grain on a long inward spiral. Scientific uncertainty enters here with gentle subtlety. The exact contribution of individual comets to the zodiacal cloud remains difficult to determine. Although comets like Hale-Bopp release significant amounts of dust, the cloud also receives material from asteroid collisions and other long-period comets. Distinguishing which grains come from which source is nearly impossible. Only took the mixing of countless dust streams over eons to make the cloud's origins a softly blended puzzle. As Hale-Bopp moves closer to the Sun and Earth, the dust tail brightens further. Backscattering of sunlight off dust grains increases, causing the dust tail to appear broader and warmer in colour than the ion tail. Earth-based observers describe the dust tail as golden or white, contrasting with the narrow blue of the ion tail. A poetic detail arises in the dust tail's curved shape, which follows the comet's trajectory and arcs away like a slow, luminous wave. Only took the balance between the comet's forward motion and sunlight's outward push to draw a broad ribbon through the sky. Dust particles continue to leave the comet at enormous rates. During its 1997 perihelion passage, estimates suggest Hale-Bopp released thousands of tons of dust per day. The dust spreads along the comet's orbit and over centuries will continue drifting, forming a meteoroid trail that persists long after the comet has returned to the outer solar system. Only took steady sublimation over a few months to create a dust path that will last for centuries. The narrator lingers on a lesser-known consequence of this dust. Some of it will eventually intersect Earth's orbit. Although Hale-Bopp itself does not produce a major meteor shower, small grains from the comet's trail can enter Earth's atmosphere, burning up as faint meteors. These meteors are rare and unpredictable, dissolving before they can draw attention. Only took a grain the size of a sand particle to trace a momentary streak across the sky before returning to darkness. A poetic detail emerges in the scattered drifting motions of these grains. Their paths are not straight lines, but slow arcs influenced by solar gravity radiation and occasional collisions with other dust particles. They form a cosmic fog too thin to see directly, yet dense enough to brighten the night sky with a faint triangular glow near the horizon. Only took a cloud of ancient dust to form one of the quietest forms of natural light on Earth. Scientific uncertainty deepens when considering the lifespan of these grains. Some persist for millions of years, others collide with planets or larger dust particles, others are ejected from the solar system entirely by gravitational encounters. The ultimate fate of any given particle remains unpredictable. Only took the complexity of orbital mechanics to make each grain's journey unique. As Hale-Bopp moves closer to the Sun, some dust grains are heated enough to release trapped gases, forming microjets of their own. Others fracture due to thermal stress. Still others remain intact, carrying organic compounds from the early solar system outward into space. The dust tail thus becomes a tapestry of different particle histories united only by their origin at the comet's surface. Only took the warming of a grain to transform it into a global traveller. The narrator shifts attention to the dust's scattering properties. Dust grains scatter sunlight more efficiently at certain angles, making the tail appear brightest when viewed from particular positions relative to the Sun and Earth. This explains why Hale-Bopp seemed dazzling in some locations and subtly muted in others. A poetic detail rises in the idea that visibility depends not on the comet alone, but on the observer's position in the solar system, a reminder that perspective shapes light. Only took the orientation of three bodies to determine the brightness of drifting grains. Meanwhile, the comet's dust production continues to shape its environment. Heavy grains fall back onto the surface, darkening regions of the nucleus. Lighter grains escape fully into the coma. Every moment, dust accumulates and disperses, forming constantly shifting layers. Only took the interplay of gravity and gas drag to determine which grains return and which drift away. The narrator observes how the dust tail stretches farther behind the comet, widening as grains disperse. The tail becomes a permanent archive of the comet's rotation activity and composition. If each grain could be traced back to its source, it would reveal precisely which jet released it, and at what rotation phase. But from a distance, the tail appears unified, a single ribbon sweeping across the sky. Only took the mixing of countless grains to create a seamless, luminous arc. Dust also plays a role in cooling the nucleus. As grains lift from the surface, they carry away heat, acting as a subtle thermal regulator. This cooling effect influences the rate of sublimation, creating feedback loops that shape the comet's behaviour. Only took the escape of warm dust to temper the heat absorbed by the comet. A quiet irony emerges. While dust tails are the most visually striking features of comets, they represent lost material erosion that will eventually reshape or reduce the nucleus. Only took the comet's brightest display to contribute to its gradual wearing away. A second irony lies in the distribution of dust. Larger, heavier grains fall behind, more slowly tracing the comet's path, while smaller grains scatter outward, quickly leaving the comet forever. Only took the tiniest grains to travel the farthest. A third irony appears in the fate of dust entering the zodiacal cloud over immense timescales. The dust becomes indistinguishable from particles released by other comets and asteroids, losing any link to Hale Bopp. Only took the blending of countless sources to erase individual origins. As Section 8 approaches its soft, unbroken end, the narrator observes Hale Bopp, continuing its journey toward the sun, shedding dust into the surrounding space with every passing moment. The dust tail broadens, the zodiacal cloud grows by an almost immeasurable amount, and each particle drifts into a future separate from the comet that released it. Nothing shifts abruptly. Nothing accelerates beyond the quiet physics at play. Only took the inward motion of a comet older than planets to enrich the interplanetary space with materials from the solar system's beginning. The narration continues with Hale Bopp as it approaches the realm, where human eyes scattered across continents and cultures will soon lift toward its glow. Yet the story remains quiet, focusing not on the moment of observation, but on the long lineage of comet watching, the patient centuries-long accumulation of knowledge that transformed comets from omens to objects of scientific understanding. The scientifically accepted fact grounding this section is that comets have been observed throughout recorded human history, with descriptions appearing in Babylonian astronomical tablets, Chinese chronicles and medieval European manuscripts. Only took the movement of a distant icy body across the inner sky to leave traces in every ancient record-keeping tradition. Hale Bopp's own 1997 apparition stands at the intersection of ancient curiosity and modern science. As the comet draws nearer to perihelion in this narration, the Earth moves into a position where it will soon see the comet clearly, yet the narration maintains its contemplative distance. From far above, the Earth appears as a quiet sphere turning beneath the comet's slow arc. People will look upward, but the comet itself remains indifferent, its behaviour governed only by the physics of sublimation radiation and orbital mechanics. Only took the coincidence of geometry to bring a comet into a viewable alignment with a world populated by observers. The narrator drifts softly into the past, lingering on a poetic detail. Ancient astronomers documented comets not as isolated objects, but as luminous intrusions upon a sky normally defined by constellations. They described comets as broom stars, guest stars star with hair or long-tailed stars. Hale Bopp's sweeping dust tail would have fit naturally into these descriptions, though the scientific explanations behind it remained unknown until the modern era. Only took the persistence of curiosity to keep comets recorded even when their nature was not understood. Scientific uncertainty has accompanied comet observations for millennia. Before Newton's laws, comets were believed to inhabit the atmosphere. Even after Halley calculated their orbits, questions about their origins, composition and structure lingered. Hale Bopp's unexpected brightness, its rich chemistry, and its unusual sodium tail revived old questions in modern contexts. Only took one exceptionally active comet to reopen debates spanning centuries. As Hale-Bopp approaches perihelion in this narration, the narrator considers the comet's visibility across civilizations. In Europe, its 1997 appearance became one of the most widely observed astronomical events of the century. Across Asia, it gleamed in early morning skies. In Africa, South America, and Oceania, it became a luminous arc above landscapes unchanged for generations. A poetic detail emerges despite the scattered nature of human life. Everyone saw the same comet moving slowly across the same sky, but filtered through differing horizons, cultures, and memories. Only took a single arc of motion to unify countless observers across Earth. Yet this section does not dwell on human reaction. Instead, it reorients toward the comet's place in the continuum of cometary appearances. Hale-Bopp joined a lineage including the Great Comet of 1811, the Great September Comet of 1882, and Halley's frequent returns. Each comet carried its own chemical signature, its own orbital story, its own interaction with solar forces. Only took Hale-Bopp's unusually large nucleus and volatile-rich layers to make it one of the brightest in recorded memory. The narrator then shifts gently to the precision of modern astronomical observation. Spectroscopy reveals the molecules escaping from the comet. Photometry records its changing brightness. Polarimetry measures the scattering angles of dust grains. Radio telescopes detect emissions from carbon monoxide. Infrared satellites record thermal features. All of this data accumulates, forming a detailed picture of the comet's behavior. Only took the quiet capture of photons across multiple wavelengths to unveil chemical details that ancient observers could only imagine, yet scientific mysteries persist. Hale-Bopp produced unusual amounts of deuterated water enriched in heavy hydrogen. This detail suggests the comet formed in extremely cold environments, possibly in the outer regions of the protoplanetary disk. But the exact temperature range and location remain uncertain, linked to models that continue to evolve. Only took the isotopic composition of a few water molecules to generate questions about the earlier solar system regions. A poetic detail deepens the mystery. Comets preserve not just minerals and ices, but the ratios of isotopes formed in star-forming clouds long before the Sun existed. Some of the molecules in Hale-Bopp bear chemical signatures matching interstellar ices, implying that part of the comet's material predates the solar system itself. Only took the collapse of a molecular cloud to trap ancient chemistry inside a nucleus that still drifts today. The narrator lingers on the comet's approach to the Sun, which brings it into the sphere of influence, where Earth-based telescopes reach peak sensitivity. Observatories from Hawaii to Chile to space-based platforms turn toward the comet, capturing spectra that reveal not only water vapor, but carbon disulfide, ethane acetylene, and cyanogen. The abundance of these molecules reveals layers within the nucleus, possibly reflecting its formation environment. Only took the heat of the Sun to release molecules that had stayed locked away since before planets existed. Still, uncertainties remain. Models disagree about how uniformly the nucleus releases gas. Some suggest outgassing comes from a few active vents. Others propose distributed sublimation across broader regions. The true structure likely lies somewhere between these extremes. Only took incomplete data to leave the comet's internal architecture partly unresolved. A gentle irony appears as the narrator contemplates Hale-Bopp's fame. Its brightness made it accessible to millions, yet its most important scientific details, molecular ratios, isotopic signatures, dust-size distributions remained invisible to the naked eye. Only took the difference between human vision and instrument sensitivity to separate popular experience from scientific insight. Another irony emerges: comets appear transient, yet their orbital paths span eras. Hale-Bopp dazzled observers for a year. Its orbit spans 2,000 years. Only took a brief passage through one epoch to be remembered in countless photographs and studies. A third irony rests in the difference between perception and reality. People saw a spectacular object, luminous and dramatic. Yet the nucleus remained hidden, dark, cold, small, the true body of the comet overshadowed by the coma it produced. only took a shell of gas and dust to mask the origin of all visible beauty. As Hale Bopp draws nearer to perihelion in the narration, its increasing luminosity creates an extended window in which Earth's rotation allows viewers from all longitudes a chance to see it. The narrator maintains a calm tone, avoiding any sense of spectacle, focusing instead on the comet's slow, measured path. The dust tail expands, the ion tail narrows and lengthens, the coma releases ancient chemistry. All of it follows physical laws that have remained constant across billions of years. Only took the steadfast constancy of physics to guide the comet into a sky filled with observers who will record it in photographs, journals, and memories. The section closes quietly as Hale Bopp continues its inward motion, still indifferent to its visibility on Earth. Dust drifts, ions realign, molecules escape. The comet's journey remains guided only by gravity, heat, and sunlight. Only took the alignment of its long ellipse with Earth's orbit to make its path visible to an entire world as the narration prepares to follow it into its brightest approach. The narration moves inward with Hale Bopp as it approaches the region where the sun's warmth reaches deeply enough to awaken molecules that have remained locked in ice for billions of years. Here the guiding sensation becomes the unfolding of chemistry, slow, ancient and precise, as the comet reveals the molecular imprint of the early solar system. The scientifically accepted fact grounding this moment is that comets contain some of the most primitive materials in existence, ices and organic compounds inherited directly from the protoplanetary disk, and in some cases from the interstellar cloud that preceded the Sun. Only took the preservation of these materials in deep cold to create a chemical archive older than any planet. As Hale Bopp nears perihelion in this narration, its coma reflects a remarkable richness of volatile molecules. Water becomes the dominant gas, but alongside it stream carbon monoxide, carbon dioxide, methane, ethane, hydrogen, cyanide, methyl alcohol, ammonia, and a suite of other simple organics. Some of these are fragile molecules that break down easily under heat, yet they survive within the comet's interior. A poetic detail emerges in imagining them trapped within tiny pockets of primordial ice microscopic caverns filled with molecules that once drifted freely in a young solar nebula. Only took those pockets remaining sealed for billions of years to release a burst of chemistry into the present. The narrator lingers on one lesser-known aspect of Hale Bopp's chemical signature, its abundance of carbon monoxide. Spectroscopic measurements indicated unusually high CO levels, especially far from the Sun. This is scientifically meaningful because carbon monoxide sublimates at temperatures too low for water to vaporize. The early detection of CO in Hale Bopp, at distances greater than 7 astronomical units, hints at internal layers rich in volatile ices. Only took a slight warming of deep layers to produce gas flows strong enough to become detectable across millions of kilometers. Yet within this detail rests a quiet scientific mystery. Why did Hale Bopp retain so much carbon monoxide despite previous passages through the inner solar system? Although the comet's exact orbital history remains uncertain, evidence suggests it has approached the Sun at least once before in the last few thousand years. Such passages typically deplete the most volatile materials near the surface. Only took one unknown aspect of the nucleus's layering or porosity to allow CO to survive in abundance. The narrator turns to isotopes, the subtle fingerprints of early nebular processes. Hale Bopp's water vapor contained elevated levels of deuterium, the heavy isotope of hydrogen. This ratio is higher than that found in Earth's oceans, suggesting that not all water on Earth comes from comets of this class. But it also indicates the comet formed in a region cold enough for heavy hydrogen to bind preferentially into ice. Only took a frigid birthplace to leave a molecular mark that remains readable billions of years later. Spectroscopic analysis also detected compounds such as formaldehyde, formic acid, and other organics believed to form through photochemical processing of simpler molecules. Some of these compounds match those found in interstellar molecular clouds, fueling hypotheses that comets preserve interstellar signatures. A poetic detail arises in imagining these molecules forming in a cloud, light years wide long before the sun existed, then becoming trapped within the icy matrix of the collapsing nebula. Only took the fall of a molecular cloud to freeze ancient chemistry into a cometary core. The narrator considers another subtlety Hale-Bopp's sodium tail. This rare feature identified through spectral mapping revealed a tail composed of neutral sodium atoms. Unlike dust or ions, sodium atoms scatter sunlight strongly at specific wavelengths, producing a glowing yellowish tail distinct from the others. Yet its exact source remains uncertain. Sodium may originate from dust grains heated near the nucleus, or from specific minerals releasing atoms when illuminated by sunlight. Only took the right blend of minerals and illumination to produce a tail invisible to most observers, yet unmistakable in spectral data. As Hale-Bopp brightens, the chemical pathways within the coma become more complex. Some molecules survive intact, others undergo photodissociation, breaking into fragments that form new compounds. Hydrogen cyanide becomes CN radicals which emit strongly in violet wavelengths. Methanol photodissociates into formaldehyde. Water breaks into OH, then O and H. Each reaction forms its own layer within the coma, creating a stratified chemical environment. Only took the steady input of sunlight to generate a miniature chemical laboratory, drifting through interplanetary space. Yet scientific uncertainty persists, especially regarding the relative abundances of complex organics. Different observations produced varying results due to the comet's changing activity and the limitations of remote sensing. Some studies reported unusually high levels of formaldehyde. Others found normal ranges. Only took slight differences in instrument sensitivity and viewing angle to create discrepancies difficult to reconcile. A poetic detail unfolds in imagining gas molecules drifting outward from the nucleus and freezing into microscopic ice grains before being warmed again by sunlight. These cycles of freezing and thawing create complex textures in the dust-mantled surface of the nucleus and influence the release of additional volatiles. Only took the simplest cycle of phase changes to shape the comet's behaviour over each rotation. The narrator shifts to a detail both subtle and revealing. Hale-Bopp emitted X-rays. Observations from the Rosat satellite detected soft X-ray emissions caused by charge exchange between fast solar wind ions and neutral atoms in the comet's coma. This process, invisible to human eyes, reveals interactions occurring on the atomic scale between solar plasma and cometary gas. Only took the collision of a solar wind ion with a neutral atom to produce an X-ray photon travelling across millions of kilometres. Yet this observation carries its own scientific uncertainty. The intensity and distribution of X-ray emissions vary with solar activity, and Hale-Bopp's brightness in X-rays exceeded expectations based on earlier comet models. Only took the complexity of plasma interactions to challenge the predictions of existing theory. As the comet approaches perihelion, the release of molecules reaches its peak. The coma becomes a vast sphere millions of kilometers wide, filled with drifting gas. The dust tail broadens, glowing gold in scattered sunlight. The ion tail lengthens, glowing blue in ultraviolet fluorescence. All of this originates from the chemical reactions occurring at the nucleus, reactions controlled by heat structure rotation and sunlight. Only took the steady warming of ancient ice to create a display visible across hemispheres. A gentle irony arises. The chemical richness that makes Hale-Bopp scientifically valuable is invisible to the naked eye. Only took the narrow bandwidths of human vision to obscure the comet's most detailed messages. A second irony rests in the fact that some molecules detected in the coma will never touch a planetary surface unless captured artificially. They disperse into space and vanish forever. Only took the comet's own outflow to erase chemical clues even as it reveals them. And a third irony lies in the interplay between destruction and revelation. Sunlight destroys molecules in the coma, but this destruction produces the spectral lines that allow scientists to determine their presence. Only took the breaking of chemical bonds to illuminate the nature of the original materials. As Section 10 draws its soft continuous close, Hale-Bopp approaches the point of closest approach to the Sun. Its chemistry becomes increasingly active. Gas flows outward in broad waves. dust escapes in shimmering plumes. Ionized molecules fill the solar wind with glowing filaments. The nucleus remains hidden, but continues releasing ice and dust forged at the beginning of the solar system. Nothing disrupts the calm. Nothing accelerates beyond nature's rhythm. Only took the convergence of heat chemistry and time to reveal a comet's ancient core to the light of a young solar system's central star. The narration moves gently outward now from the inner chemistry of the coma, and begins following Hale Bopp back along the immense arc of time that set its origin, letting the comet's present glow become only one moment in a lineage stretching to the farthest reaches of the solar system. Here the guiding sensation becomes distance, not the distance travelled during this apparition, but the primordial distance from which Hale Bopp was sent. The scientifically accepted fact grounding this section is that long-period comets like Hale Bopp originate in the Oort Cloud, a spherical reservoir of icy bodies extending tens of thousands of astronomical units from the Sun, shaped by gravitational scattering in the early solar system. Only took the tumultuous interactions with giant planets billions of years ago to send countless small worlds into a distant dark sphere enveloping the solar system. As the narrator drifts conceptually toward the Oort Cloud, the scale expands dramatically. The region where Hale Bopp formed its earliest identity lies so far from the Sun that the star appears no brighter than a distant, unusually luminous point of light. Their temperatures fall close to absolute zero. Motion proceeds so slowly that a full orbit around the Sun takes millions of years. A poetic detail emerges in imagining this realm as a quiet, fragile lattice of ancient frozen bodies drifting like soft embers in a cold, unlit ocean. Only took the feeble gravity of the Sun at that distance to hold 1 trillion icy fragments in a barely bound population. The narrator considers the Oort Cloud's formation. In the early solar system, Jupiter, Saturn, Uranus and Neptune scattered vast numbers of icy planetesimals outward. Some were ejected into interstellar space entirely. Others slowed just enough to remain gravitationally bound, settling into near-spherical orbits. This dynamic scattering explains the cloud's shape, not a flat disk like the Kuiper Belt, but a vast shell. Only took a few million years of gravitational encounters to transform a disk of icy seeds into a sphere of distant wanderers. Yet scientific uncertainty lies softly across the Oort Cloud, for it has never been observed directly. Its existence is inferred entirely from the behaviour of long-period comets like Hale Bopp. No telescope has resolved its objects. No spacecraft has ventured anywhere near its lower boundary. Only took the limitations of distance to cloak a structure so large it dwarfs every planetary orbit. Hale Bopp's history within this cloud traces back through countless revolutions around the Sun. Each orbit lasted so long that the positions of nearby stars shifted noticeably between perihelion passages. Passing stars occasionally nudged Hale Bopp's orbit, slightly altering the timing of its inward journeys. Only took the quiet drift of stellar neighbours to influence a comet's path across millions of years. The narrator drifts farther outward in thought into the galactic environment influencing the cloud. The Sun travels through different regions of the Milky Way over its 225 million-year orbit around the galactic centre. Each new region exposes the Oort Cloud to subtle variations in gravitational fields, interstellar clouds and passing stars. These interactions can send objects inward or outward, shaping the long-term flux of comets. Only took the Sun's motion through the galaxy to create the gentle tides that disturb the cloud's population. A poetic detail arises when imagining the Oort Cloud under the influence of the galactic tide, a faint, almost imperceptible gravitational gradient from the Milky Way's disk that slowly changes cometary orbits. Though the force is unimaginably weak, its effect accumulates over millions of years, encouraging some comets to drift inward. Only took the soft pull of distant stars and nebulae to subtly reshape the trajectories of worlds frozen at the galaxy's edge. In this conceptual space, Hale Bopp is but one of trillions. Some Oort Cloud bodies will never leave their distant orbits. Others will gradually drift inward, captured by slight inclinations of their trajectories. A passing star may perturb part of the cloud, sending dozens of objects inward over extended intervals. Only took the approach of a star within a few light years to initiate a small comet shower. Scientific uncertainty deepens in discussions of the cloud's true population. Estimates vary by orders of magnitude. Some models propose hundreds of billions of bodies, others suggest trillions. The difficulty arises because only a fraction of Oort Cloud objects ever become visible comets. Most remain in the dark, silent and unmoving relative to any observable timescale. Only took the rarity of inward perturbations to keep the cloud's full size obscured. The narrator observes how Hale-Bopp's journey inward began long before it became visible. A slight perturbation, perhaps from a passing star tens or hundreds of millions of years ago, nudged its orbit enough to send it slowly drifting toward the sun. The drift took ages. At first, the change in trajectory was almost imperceptible. But over millions of years, the comet moved gradually inward, beginning the long descent that would eventually bring it into the inner solar system. Only took an almost invisible stellar push to redirect a body the size of a city across a span of space, larger than the distance between stars. A poetic detail emerges in imagining the Oort Cloud's silence. No collisions, no impacts, no eruptions, only the slow orbiting of frozen nuclei through a space so wide that each object is separated from its nearest neighbour by enormous distances. Only took the low density of the region to ensure that comets could drift for billions of years without ever touching one another. As Hale-Bopp left the Oort Cloud and began its movement inward, the sun gradually brightened in its sky. For millions of years, the comet drifted through regions where the sunlight's warmth could barely reach its surface. Sublimation did not begin until it breached the realm inside Neptune's orbit. But even before that, the sun's faint glow shaped its path, providing the gravitational anchor that kept it tied to the solar system. Only took the weak but persistent gravity of the sun to ensure that Hale-Bopp would one day return. The narrator traces the comet's long descent through the outer solar system. Past the orbits of scattered Kuiper Belt objects, past regions where dust is sparse and space nearly empty, the comet moved gradually into warmer realms. Each step inward accelerated, guided by Kepler's laws. Only took the geometry of an ellipse to convert the slow drift of aphelion into the swift approach of perihelion. A gentle irony arises. Hale-Bopp spent more than 99% of its orbital period in the deep cold of the Oort Cloud, yet the entire visible display that captivated Earth lasted only a few months. Only took millennia of darkness to produce a brief moment of light. A second irony appears in the role of passing stars. While their nudges often send comets inward, they can also eject comets permanently. The same forces that delivered Hale-Bopp to the inner solar system could just as easily have cast it into interstellar space long ago. Only took a slight difference in trajectory to decide whether the comet would ever be seen. A third irony lies in the cloud's nature itself. It contains the solar system's oldest materials, yet it is the least observed and least understood region. Only took the great distance of its objects to ensure that the most ancient remnants remain hidden. As Hale-Bopp nears the inner solar system in the narration, its ancient past in the Oort Cloud becomes only background, an origin point far removed from its current illuminated state. But the shape of its orbit, the composition of its ice, the richness of its chemistry and the vigour of its activity all arise from that distant frigid realm. The Oort Cloud remains invisible, unmeasured, inferred only by comets like this one, which serve as emissaries from a region too remote for direct exploration. Section 11 draws slowly to its quiet close, with Hale-Bopp continuing inward, carrying within its nucleus the frozen signature of the early solar system and the even older imprint of interstellar chemistry. Nothing shifts abruptly. Nothing deviates from the slow pattern established billions of years ago. Only took the long descent from the Oort Cloud to let the comet finally reveal itself in the warm glow of the sun. The narration continues with Hale-Bopp as it approaches the deepest point of its inward journey, letting the comet's long descent from the Oort Cloud come into quiet contact with the immense gravitational influences of the inner solar system. Here, the guiding sensation becomes the shaping of motion, the way gravity from the Sun and the planets subtly bends, accelerates and redirects the comet's path without ever disturbing its essential stillness. The scientifically accepted fact grounding this moment is that a comet's orbit is governed by Keplerian motion, with gravitational interactions from massive planets occasionally altering its period or inclination. Only took the slow pull of celestial mechanics to determine the comet's long ellipse. As Hale-Bopp enters the region where Jupiter's influence becomes significant, its orbit responds slightly. Jupiter, the largest planet, exerts a gravitational force that shapes the long-term stability of cometary orbits. For many comets, encounters with Jupiter result in dramatic changes, either sending them into the inner solar system more frequently or ejecting them entirely. A poetic detail emerges in imagining these interactions as quiet, distant dances between bodies that never touch their motions, intertwined across immense distances. Only took a moment of alignment in deep space to reshape trajectories lasting thousands of years. Yet Hale-Bopp's path remains relatively unaffected during this passage. Its enormous orbital energy accumulated from a descent of many thousands of astronomical units dwarfs the gentle perturbations possible during this perihelion cycle. The comet passes safely through the realm of the giant planets, carrying forward its stored momentum. Only took the geometry of its approach to prevent it from becoming one of Jupiter's captured wanderers. Scientific uncertainty still lingers in the details of small perturbations. Jupiter's influence may change Hale-Bopp's future orbital period slightly, perhaps from roughly 2,500 years to closer to 2,300 or 2,400 years, depending on subtle gravitational interactions. Tiny differences in trajectory, often below observational resolution, accumulate over millennia. Only took the faintest shift in angle to affect the timing of its return by centuries. The narrator lets the scene expand to include the other planets, each exerting its own gravitational pull, though far weaker than Jupiter's. Saturn contributes a gentle tug, modifying the orbit in minuscule ways. Uranus and Neptune lie too far to affect this passage, but their resonant histories shape the comet's earlier scattering billions of years ago. A poetic detail emerges in the idea that these giant planets, spinning slowly in their own orbits, act like distant gatekeepers through which comets must pass to reach the warm light of the Sun. Only took the slow patrol of these massive worlds to influence the motion of icy visitors. Meanwhile, Hale-Bopp feels the Sun's pull intensify as it nears perihelion. The comet accelerates dramatically following Kepler's second law. It sweeps out equal areas in equal times, which means it moves fastest when closest to the Sun. The velocity at perihelion rises sharply, tens of kilometers per second, yet the narration remains calm, focusing not on speed, but on the inevitability of the gravitational arc. Only took the simple geometry of an ellipse to turn a slow drift into a swift descent. A quiet scientific mystery lies in the exact distribution of mass within the nucleus. Although the nucleus is estimated to be around 40 kilometers across its internal density, porosity and structural complexity remain unknown. These factors subtly influence its gravitational interactions with the Sun and planets. Only took the inaccessibility of a distant icy core to leave its internal structure unresolved. The narrator shifts toward the interplay between orbit and outgassing. As Hale-Bopp approaches, perihelion sublimation becomes vigorous enough to create jets that exert tiny reactive forces on the nucleus. These forces can alter rotation rates and even modify the orbit slightly. Although such effects are small, they are measurable for some comets. In Hale-Bopp's case, observations recorded changes in rotational period from roughly 11 hours to a slightly shorter value. Only took the release of ancient gases to apply tiny thruster-like nudges. A poetic detail unfolds in imagining each jet as a breath escaping from deep within the nucleus, a gentle exhalation that subtly shifts the comet's orientation. The rotation gradually accelerates or decelerates depending on the direction of outgassing, creating a slow interplay between the physics of sublimation and celestial motion. Only took a plume of vapor to modify a world's rotation. The narrator steps back to consider Hale-Bopp's long-term trajectory after perihelion. Once it rounds the Sun, its velocity will diminish as it ascends the long ellipse back toward the outer dark. The orbit carries the comet far beyond the planetary region into a realm where the Sun's pull again becomes faint. Over time, gravitational interactions will shape the next return. A quiet irony emerges here. The comet's brief passage near the Sun, so bright and fleeting, determines the details of a journey lasting thousands of years. Only took a few months of warming to influence millennia of cold travel. A second irony reveals itself in the interplay between light and gravity. The Sun's brightness creates the spectacular tails seen from Earth, yet it is the Sun's gravity that controls the orbit, not the sunlight. Only took the invisible force to guide the comet, while the visible light merely revealed it. A third irony rests in the fact that while the planets exert small but meaningful influences on Hale-Bopp's orbit, the comet's path is so elongated that its outermost regions lie far beyond the planet's reach. Only took one journey through the planetary zone to determine the orbit, even though the comet spends nearly all of its life far beyond it. The narrator observes how Hale-Bopp's trajectory reaches its deepest inward curve. The Sun appears enormous now from the comet's vantage, though still only a luminous disk framed by streaming gas. The tails stretch outward in response to solar radiation and the solar wind. The dust tail glows warm, the ion tail glows cold, the sodium tail gleams faintly in narrow wavelengths. All of these features follow the comet's orbit, but reveal nothing of the forces shaping that orbit. Only took the Sun's heat to create visible beauty, while the Sun's gravity shapes invisible motion. As perihelion passes, the comet begins to slow, though imperceptibly at first. The outward climb begins gently. Its path remains smooth, defined by centuries of inertia and the gravitational boundaries of the solar system. Hale-Bopp will soon return to regions where light fades and sublimation weakens, then cease entirely. Outgassing jets will quiet, dust production will diminish, the nucleus will cool. Yet the orbit will remain a long ellipse extending thousands of astronomical units outward. Only took the simplest gravitational rule to bind the comet to a trajectory it will follow long after observers forget its passage. A poetic detail arises as the narrator imagines the comet's path traced like a faint elongated ribbon through the solar system, a curve repeated once every few thousand years, shaped by forces unchanged for billions of years. The ribbon intersects the planetary region only briefly, then stretches outward into cold darkness, where only the slow rotation of the nucleus marks the passage of time. Only took the faint echo of sunlight to light one moment of that curve. Scientific uncertainty reappears as the narrator considers the few possibilities for future perturbations. Another passing star in the distant future may alter Hale-Bopp's orbit significantly, or a slight interaction with Jupiter on a future return may reshape its period. These uncertainties reflect not the unpredictability of physics, but the inability to model every future gravitational encounter across thousands of years. Only took the immensity of timescales to cloud the precision of prediction. Section 12 moves toward its quiet conclusion as Hale-Bopp continues through perihelion, beginning the long outward climb. The narrator remains focused on the interplay between gravity motion and time. The comet follows a trajectory set billions of years ago, influenced by the architecture of the planets and the faint pull of distant stars. Nothing distracts from this motion. Nothing disrupts its patient arc. Only took the quiet rhythm of celestial mechanics to bring an ancient comet into the inner solar system, before guiding it gently back outward into the long night. The narration follows Hale-Bopp now as it begins the long unhurried transition from its brightest state back into the deeper quiet of the outer solar system, letting the intense energy of perihelion soften into the steady cooling that always follows. Here the guiding sensation becomes dissipation, the way heat gas and dust gradually fade as the comet retreats from the Sun, revealing once more the darker, quieter nature of the nucleus beneath. The scientifically accepted fact grounding this moment is that a comet's activity decreases sharply as it moves away from the Sun, because sublimation rates depend strongly on solar heating. Only took the widening of distance for the comet to begin shedding its luminous armour. As Hale-Bopp drifts outward, its outgassing gradually slows. Molecules that once escaped in torrents begin to diminish. The coma shrinks, becoming less dense and less extended. The elaborate chemical reactions that dominated its inner regions fade as sunlight weakens. A poetic detail emerges in this cooling. The coma's outer edges, once bright and full of motion, begin dissolving into invisible thinness, like mist evaporating in reverse. Only took the comet's retreat to make the once enormous cloud gently disappear. The dust tail responds more slowly to the diminishing heat. Dust grains continue drifting outward for some time, forming long, diffuse plumes. But the fresh supply begins to dwindle. Larger grains fall behind and begin dispersing. Smaller grains continue their long trajectories into interplanetary space. Only took the soft reduction in sunlight to change the dust tail from a brilliant arc into a broader, more tenuous veil. Scientific uncertainty lingers in the exact mechanisms that govern the cutoff of activity. Different regions of the nucleus respond to cooling at different times. Some layers retain enough heat to continue sublimating slightly, even at moderate distances. Others shut down almost immediately. The location of active vents, the depth of volatile rich layers, and the thermal properties of the surface all shape this transition in ways that remain partly unresolved. Only took the subtle combination of temperature, structure, and rotation to leave the details unclear. As sunlight weakens further, the ion tail begins to fade more quickly than the dust tail. Ion production depends on ultraviolet radiation, and without strong sunlight, the ions recombine or dissipate into the solar wind. The once sharply defined blue filament becomes faint, then nearly invisible. The solar wind continues streaming outward, but the coma no longer provides enough charged particles to form a coherent tail. Only took the dimming of light to erase a structure millions of kilometers long. A poetic detail emerges in the final moments of the ion tail, even as the primary structure fades. Small clumps of ionized gas remain embedded in the solar wind, drifting away along magnetic field lines. These tiny fragments, invisible from Earth, represent the last breaths of plasma released at perihelion. Only took a few scattered ions to carry the memory of the comet into distant heliospheric currents. The narrator lingers on the cooling of the nucleus. As outgassing slows, the surface begins to darken again. Dust settles back onto certain regions, forming a thin insulating layer. Thermal waves from perihelion gradually move inward, but the nucleus cools more quickly than heat can penetrate deeply. This means much of the comet's interior remains almost unchanged, preserving its ancient chemistry. Only took a few weeks of outward motion to return temperatures toward their deep frozen state. Another quiet scientific mystery appears: how much mass did Hale-Bopp lose during its passage? Estimates vary based on the intensity of outgassing and dust release. Some models suggest the comet shed a small fraction of its total mass. Others propose more substantial losses, especially given its unusually strong activity far from the Sun. Only took the difficulty of measuring dust from a distant nucleus to leave total mass loss uncertain. As Hale-Bopp continues outward, its spin stabilizes. Earlier jets altered the rotation period slightly. Now those effects diminish. The nucleus settles into a more consistent rotation rate, yet its orientation may continue drifting slowly, influenced by subtle torques from uneven cooling. A poetic detail emerges in imagining the nucleus turning slowly in silent space, its darkened surface returning to its ancient equilibrium as heat escapes into the void. Only took the return of darkness to steady the comet's internal rhythm. Dust trails left in the comet's wake begin to disperse further. Some parts of the trail linger for centuries along the comet's orbit, forming faint meteoroid streams. Others drift outward, becoming part of the zodiacal cloud. Only took the flight of tiny grains to enrich interplanetary space for millennia. The narrator shifts toward Earth's perspective at this stage. Long after the comet begins to fade from the sky, its dust continues to drift in the inner solar system. Earth may encounter traces of this material, occasionally producing a few faint, unpredictable meteors that burn silently in the upper atmosphere. These are not part of any formal meteor shower. They are individual wanderers. Only took a single grain to leave a fleeting streak across a quiet night. A soft irony appears. Hale-Bopp's outward trajectory holds no dramatic moment of departure. While its approach dazzled millions, its fading went largely unnoticed, happening slowly, quietly, without spectacle. Only took the natural balance of motion for a world-brightening comet to vanish without ceremony. A second irony emerges. The comet becomes more scientifically interesting as it fades. Freshly exposed layers cool and contract, perhaps showing subtle shifts in surface features detectable by infrared observation. But by then, few telescopes continue tracking it closely as attention shifts to other objects. Only took the loss of visible brightness to reduce scientific focus at the moment when deeper structural changes might be occurring. A third irony lies in the retreat itself while the comet grows smaller. In apparent size, its orbit expands outward into distances far greater than those covered during its visible phase. Only took the outward slope of the ellipse for the comet's journey to grow more immense even as it becomes invisible. As Hale-Bopp moves beyond the orbit of Mars, its activity becomes minimal. The coma contracts to a thin envelope. The gas production rate drops by orders of magnitude. The tails become vestiges. Eventually, the nucleus returns to a state indistinguishable from an inert asteroid, except that its composition remains dominated by ice. Only took the cooling of space to return a luminous visitor to silent anonymity. A poetic detail arises in imagining this retreat. Sunlight fades gradually, not in any abrupt boundary, but as a gentle dimming across millions of kilometers. Shadows sharpen, ice becomes brittle. The nucleus re-enters a realm where time feels slower, distances stretch endlessly, and every rotation occurs in cold that has persisted since the dawn of the solar system. Only took the outward journey to restore the ancient quiet. Scientific uncertainty deepens when considering the exact path Hale-Bopp will follow over the next thousands of years. Tiny gravitational nudges slight out gassing forces, and the unpredictable passage of nearby stars will all shape its next return. Models provide estimates, but over millennia, small initial uncertainties magnify. Only took the steady accumulation of unseen influences to cloud the comet's long-term future. Yet the overall trajectory remains clear. Hale-Bopp will climb outwards, slowing steadily, as the sun's gravity weakens. Eventually it will reach aphelion, a point so distant that radio waves from Earth would take days to reach it. There, in the remote outskirts of the solar system, it will linger in deep cold. Only took the perfection of its ellipse to define a path leading back into the darkness from which it once emerged. Section 13 closes gently as Hale-Bopp's brightness dims and its tails dissolve into memory. The comet resumes the patient silence that has always defined most of its existence. Activity dwindles, heat fades, motion continues without urgency. Only took the long outward slope of its orbit to guide the comet from its most luminous moment back toward the resting place of ancient ice, where time stretches almost without meaning, and the sun becomes only a distant glow. The narration follows Hale-Bopp deeper into the expanding coolness of its outward journey, letting the comet transition from a luminous visitor into a quiet remnant again, its surface and surroundings returning gradually to the slow equilibrium of deep space. Here, the guiding sensation becomes the quieting of processes that once roared with activity, the settling of dust, the cooling of ice, the lengthening of shadows, and the return of the nucleus to a condition that resembles timeless sleep. The scientifically accepted fact grounding this moment is that beyond a certain distance from the Sun, usually around 3 to 4 astronomical units, water ice can no longer sublimate in significant quantities, causing the comet's activity to drop nearly to zero. Only took the waning of sunlight to silence the engines that shape the comet's spectacular display. As Hale-Bopp crosses this threshold, its coma contracts further. The once massive envelope of gas shrinks to a thin haze barely clinging to the nucleus. Molecules that once filled a sphere millions of kilometers wide now drift away and are not replaced. A poetic detail emerges in imagining the fading coma as a breath exhaled long ago dispersing across the solar wind until nothing remains but the memory of motion. Only took the slow diminishing of heat to end a process that had persisted for months. The dust tail fades more gradually, its broad stream now consisting solely of particles released earlier. These grains continue drifting, influenced by sunlight and gravity, but no new dust joins them. The tail becomes diffuse, wispy, and eventually indistinguishable from the general zodiacal cloud. Only took the delay in dust dispersal to let the tail linger longer than its source. Scientific uncertainty appears in the thermal behavior of the nucleus. The outer layers heat and cool on seasonal timescales defined by the comet's orbit, but the interior responds much more slowly. As Hale-Bopp recedes, the thermal wave generated during perihelion will continue to penetrate inward for months or even years, subtly altering the structure of pockets, cavities, and deeper ices. But exactly how far this heat travels and how it affects internal chemistry remains unknown. Only took the inaccessibility of deep layers to keep these processes hidden. As the nucleus cools, dust settles upon its surface, forming a patchy mantle. Some of this dust originated from deeper layers exposed during sublimation. Other grains come from fallback particles that did not achieve escape velocity during outgassing, and instead returned gently to the surface. A poetic detail emerges in imagining these grains settling like a thin, uneven snowfall, darkening some regions while leaving others untouched. Only took the weakening of jets to allow dust to fall back into quiet patterns. The narrator lingers on the changing rotation of the nucleus. Earlier jets created small torques, speeding up or slowing down the rotation. Now with activity nearly gone, the nucleus settles into a more stable spin. Its rotation becomes a slow, persistent rhythm unperturbed by external forces. Only took the end of outgassing to restore rotational calm. A gentle irony arises here. The quiet, dark state of the nucleus is its natural condition, the state in which it exists for more than 99% of its orbital lifetime. Only took the brief proximity to the Sun to create a spectacle, visible across continents, while the comet's true form remains mostly unseen. Another irony lies in the transition itself. While the comet appears to be dying or fading, it is actually returning to the familiar equilibrium it has maintained for billions of years. Only took the decrease in sunlight to make the comet seem like it was ending, when in fact it was simply returning to normal. A third irony surrounds the comet's visibility from Earth. During its approach, millions watched it rise and set. During its departure, far fewer followed its fading arc. Yet the outward journey is just as long, just as significant, and just as governed by the same laws of motion. Only took the fading of brightness to shift human attention away, though nothing about the comet's story diminished. As Hale-Bopp travels farther from the Sun, another subtle transition begins. The dominance of carbon monoxide and carbon dioxide sublimation decreases as even those volatile species become dormant. Their activity can persist at greater distances than water, but eventually even these ices stop vaporizing. The comet enters a realm where temperatures drop to tens of degrees above absolute zero, and sublimation becomes negligible. Only took the return to this cold for the comet's chemistry to fall into stasis. Scientific uncertainty deepens around this distant region. Researchers debate how long volatile ices survive in the outer layers of long-period comets, especially after close solar passes. Some models suggest that repeated perihelion encounters lead to crust formation, hardened surfaces that trap deeper volatiles. Others propose that the porous, fluffy nature of cometary material allows sublimation to continue from internal pockets long after the surface freezes. Only took the porous complexity of the nucleus to leave the fate of its ices undetermined. The narrator shifts attention to the comet's broader environment. As Hale-Bopp moves past the orbit of Jupiter, the Sun's gravity begins to weaken noticeably, though still strong enough to hold the comet. Space grows more sparse, dust becomes rarer, the solar wind thins, radiation becomes less intense. The background becomes dominated once more by the quiet of the outer solar system. A poetic detail emerges in the dimming sunlight, no longer a warm disk, but a pale star whose brilliance no longer shapes the comet's behaviour. Only took the widening distance to transform the sun from a source of heat into a point of light. Yet even in this calm, gravitational forces remain active. Hale-Bopp continues climbing the long slope of its orbit, slowing slightly each day. Its path is predictable. It will travel thousands of astronomical units outward, reaching a distance where the sun's gravitational pull becomes so faint that even nearby stars exert comparable influence. Only took the balancing of forces to define a trajectory that stretches across millennia. A quiet scientific mystery lingers in the comet's long-term stability. Whether Hale-Bopp will return in roughly 2,000 years or be perturbed by passing stars remains unknown. Gravitational models project likely scenarios, but cannot account for every future influence. Only took the vastness of time to blur the boundary between certainty and possibility. The narrator reflects on how Hale-Bopp, now fading, leaves behind no permanent imprint on the inner solar system except for dispersed dust. It does not alter orbits. It does not change climates. It does not influence tides. Its impact is purely observational, a record in photographs, journals, and memory. Only took the quiet passing of a cosmic traveller to remind observers of the long cycles that shape the solar system. A poetic detail rises near the end of this section. As the comet drifts outward, its shadow stretches behind it, in a direction opposite the sun, an elongated silhouette cast upon space rather than upon any surface. The shadow has no meaning without dust, yet, for a moment it represents the comet's final interaction with sunlight during this passage. Only took the fading of illumination to make the shadow seem longer than the comet's own visible tail. As the narration brings Hale-Bopp deeper into the outer dark, the comet becomes almost entirely inactive. Rotating slowly, cooling steadily, it returns to the dormant state that defined its existence before this journey. The dust that once surrounded it falls away. The coma becomes imperceptible. The nucleus remains alone, a dark icy remnant drifting through a realm where change is measured in eons rather than hours. Section 14 settles into quiet as Hale-Bopp continues outward, slowing, gently approaching the great arc that will eventually carry it far from the sun. Nothing pushes it now except inertia and the faint gravitational pull that binds it. The comet's brilliant display becomes a memory, the nucleus returning to the cold from which it emerged. Only took the long outward slope of its orbit to guide the comet back toward the distant silence, where sunlight fades into starlight and the vastness of the solar system thins into the beginnings of interstellar space. The narration continues with Hale-Bopp as it slips farther into the dim, widening outskirts of the solar system, letting the last traces of its recent activity dissolve into the cold. Here the guiding sensation becomes reunion, the gradual return of the comet to the deep quiet from which it first emerged, the restoration of its long-held equilibrium in a region where heat fades, gas settles, and the rhythm of time becomes slow enough to resemble stillness. The scientifically accepted fact anchoring this moment is that comets spend the overwhelming majority of their orbital lifetimes far from the sun, in regions where temperatures hover only a few dozen degrees above absolute zero, and where any trace of sublimation becomes negligible. Only took the outward drift to restore the deep cold that defines a comet's existence. As Hale-Bopp recedes beyond Jupiter's realm, the sun grows weaker day by day. Light arrives softer, more diffuse, spread across a distance that expands with every passing hour. Sublimation has nearly ceased. No new jets form. No fresh molecules erupt from the surface. The coma shrinks to an imperceptible skin of gas, then vanishes entirely. A poetic detail arises in this disappearance. What was once a luminous sphere millions of kilometers wide now contracts to nothing more than a thin veil of invisible molecules trailing faintly behind the nucleus, like the last vapor escaping a cooling ember. Only took the subtle dimming of sunlight to extinguish the glow. Dust too falls into its own quiet pattern. Larger grains released earlier continue drifting along the orbital path, but none return to the comet. The nucleus is now too cold to produce new grains, and the gravitational pull is too weak to reclaim those already cast into space. Only took the temperature drop to end the exchange between nucleus and dust forever on this orbit. Scientific uncertainty settles softly around the nucleus's internal structure. The heat generated during perihelion will continue to migrate inward long after the surface cools. Over months and years, this thermal wave will slowly penetrate deeper layers, modifying the state of ices that have remained untouched for millions of years. But exactly how these layers respond, whether they fracture, slightly densify, contract, or remain unchanged, remains unknown. Only took the thickness of the crust and the porosity of the interior to conceal the fate of ancient volatiles. The narrator lingers on rotation, the comet's one persistent motion besides its orbit. Earlier talks from jets altered its spin, subtly leaving the nucleus with a new rotational period. Now free from asymmetrical forces that rotation stabilizes. The nucleus turns steadily, its surface marked by dust-covered plains, collapsed pits and remnants of vents. A poetic detail emerges. The rotation becomes a slow, metronomic ticking that counts not hours or days, but the quiet persistence of an object older than any planet. Only took the ending of outgassing to re-establish this ancient rhythm. A gentle irony reveals itself here. Although the comet's glowing tails and expansive coma defined its visibility from Earth, those features existed only because of temporary heating. The true comet, the dark, icy nucleus, is nearly invisible, the smallest and least luminous part of the entire apparition. Only took the fading of sunlight to reveal that the spectacular display was merely a surface effect. Another irony rests in the scaling of time. Hale-Bopp's luminous journey through the inner solar system lasted months. Its descent from the Oort Cloud took millions of years. Its return will take another few thousand. Yet observers remembered only the months. Only took the narrowing of human attention to focus on one bright moment in a cycle spanning geological eras. A third irony lies in the comet's trajectory itself. Although its brilliant display seemed intentional or directed, nothing in its motion is purposeful. Every part of its orbit follows naturally from initial conditions set billions of years ago. Only took the conservation of momentum to create a path that appears deliberate but is entirely the product of ancient forces. As Hale-Bopp moves past Saturn's orbit and toward Uranus's distant track, the physical environment shifts subtly. Solar radiation weakens further. Cosmic rays become a more significant source of particle interactions at the surface. Micrometeoroids remain sparse but present, occasionally striking the nucleus and chipping away tiny fragments. These impacts are rare, but over millions of years they contribute to the slow erosion of cometary surfaces. Only took the faint rain of interplanetary particles to shape the comet across ages. The narrator follows the comet's outward trajectory as it enters the realm where the sun becomes simply another star, still brighter than all others, but no longer radiating enough warmth to influence the comet's surface. Hale-Bopp cools toward its natural equilibrium temperature approaching tens of kelvins. All surface processes slow to near zero. Only took the return to deep dark to freeze the nucleus in time once more. Scientific uncertainty deepens concerning the comet's distant future. The orbit will carry it far beyond the planets into regions where gravitational influences from nearby stars or interstellar clouds may subtly alter its trajectory. Models project its return in roughly 23 centuries, but even small perturbations can alter that timeline significantly. Only took the slow drift of stars passing within a few light years to shift the comet's path across millennia. A poetic detail emerges in imagining the comet reaching aphelion, its farthest point from the sun. At that distance, the sun's light will resemble a bright star hardly distinguishable from others in the sky. The comet will drift slowly, its velocity near zero, tracing the faint curve of its orbit nearly imperceptibly. Only took the geometry of an ellipse to create a point in space where motion becomes almost indistinguishable from stillness. As Hale-Bopp moves outward, all memory of its luminous display becomes irrelevant to the comet itself. It carries no record of its brightness, no imprint of the millions who observed it. It continues along its orbit, unchanged by attention, unchanged by perception. Only took the constancy of physical laws to separate the comet's path from the act of observation. The narrator lingers on the dust trail the comet leaves behind. Although most grains disperse widely, some follow the comet's orbit closely enough to persist for centuries or even millennia. These grains may gradually form a tenuous meteoroid stream. Earth may one day encounter traces of it generating faint irregular meteors, but the trail remains too sparse to form a major shower. Only took the release of a few particles to plant seeds of future streaks in the night sky. As the comet retreats farther, still passing beyond the orbit of Neptune, the solar wind becomes faint but not absent. It continues to interact weakly with the cometary surface, though without gas to scatter, the comet remains inert. Radiation pressure no longer shapes any tail. Only took the end of sublimation to reduce the comet to a solitary darkened body drifting silently outward. A final quiet scientific mystery touches the heart of this section. What lies at the very centre of the nucleus models suggests a mixture of ice dust, organics and voids. But direct measurements are impossible. The heart of Hale Bopp remains untouched, unheated, unaltered. Only took the cold of billions of years to keep this ancient chemistry perfectly preserved. Section 15 gently nears its close as Hale Bopp continues the long arc of its outward journey. The comet becomes smaller, darker, quieter, returning to the vast region where sunlight grows thin and time stretches across uncounted ages. It carries within it secrets of the early solar system and echoes of interstellar chemistry, yet reveals nothing as it drifts. Nothing disrupts its path. Nothing hastens its motion. Only took the gentle, unbroken rules of gravity and cold to guide the comet from brilliance back into stillness, where it will remain for centuries before warming once more. The narration loosens now, letting the long arc of Hale Bopp's journey soften into a quiet without direction or urgency. Out here, where the sun is only a pale point in a wide darkness, the comet drifts in a calm that feels older than memory. The scientifically accepted fact that comets spend nearly all of their existence in these distant regions becomes almost a whisper, a reminder that brightness is only ever a brief interruption in a life defined by cold. Only took the faint withdrawal of sunlight to dim a world that had once stretched luminous tails across Earth's sky. A poetic detail settles gently into view, the nucleus dark and silent, turning slowly in a cold so deep that even time seems to slow around it. Each rotation is steady, unhurried, carrying no trace of the warmth or activity that shaped its brief passage near the sun. Only took the quiet of distance to restore a rhythm older than planets. A small uncertainty drifts in the background, unbothered and unresolved, whether the comet will return unchanged in 23 centuries, or whether a passing star will alter its orbit subtly, or whether it will slip into a new trajectory across the interstellar dark. The future remains open in a way that feels natural rather than unfinished. Only took the vastness of time to make certainty unnecessary. The ironies that carried through its journey soften now into a gentle stillness. A comet that blazed across a world becomes almost invisible again. An object shaped by sunlight retreats into a place where light barely reaches. A visitor observed by millions becomes a solitary traveller drifting where no gaze can follow. Only took the long outward path to return it to the quiet it has always known. Here in this cooling distance, nothing rushes, nothing resolves, nothing needs to. The orbit stretches into slow darkness. The sun becomes a distant shimmer lost among stars. Dust drifts. Ice sleeps. Motion continues without effort. And the comet, older than any observer who watched it pass, settles once more into the deep, patient stillness that awaits all things far from the warmth of a star.